Okay, thanks for bearing with me during the break in videos. I'm still kind of figuring out how to use my screen recording thingy. So we are talking about residuals. How do you approach a question about residuals? What are residuals? And I think Dr. Henry has done an awesome job giving you plenty of information about residuals. Definitely go back to that, read through it, make sure you understand it. I'm going to talk a little bit about how I approach the concept of residuals and how I approach a question about residuals. And so anytime I see the word residual, I'm thinking of a graph like this. In this graph, we have our points, which are our observations, our regression line, and we have our X and Y axis. And so before I even think about numbers that I might use for my answer, I will sketch out any part of this that I already have information for. I will try to figure out what is my predictor, what is my Y, what direction is the slope going in. I'll sketch that out, and that helps me keep oriented for all the following questions that might be about this data. And so in this case, we can see that the residual is going to be this distance between the observation and the regression line. Now, this is really important because this is helping us understand how good of a model we have. If we have a lot of variance and really big residuals, then our model isn't explaining as much of the variance as if we had smaller residuals that were closer to the line. And I think everyone is really getting the hang of that concept. It just tends to be calculating that residual that people are having a hard time with. And so to calculate the residual, we are going to take a look at quiz 6, this question about one of the runners having a marathon time of 250 minutes with 30% humidity, calculate the residual. And so if you remember from quiz 6, marathon time is going to be our y-axis. And so if I were you, I would literally be drawing a little x and y axis and put marathon time on the y. And so for this, we're being given a marathon time. Now, if I would have said predicted marathon time, then I'm going to visualize that as a piece of this line. If it was a predicted marathon time, then that's going to be on your regression line. But I'm not saying predicted. I'm saying this is their marathon time. And so thinking of that in my little drawing, I would draw a dot, not on the regression line. I hope that makes sense as I'm explaining it. And so now I know my actual marathon time on a day with 30% humidity, and I need to calculate the residual. So over here, we have some elements of our regression equation. We have the intercept. That's a great place to start. So I would literally just be drawing a little plus on my paper next to the intercept because I know that's the first step of the regression equation. Next, I'm going to need a slope, a B1. And in this case, we can see that humidity is the variable we're going to be changing, and so the humidity estimate is the slope that we're going to use. And so when I approach a test question like this, I just write it out on the test next to the intercept. I would go intercept plus slope times the x value that you're given, which in this case is 30. Use your little calculator, and that'll give you the predicted value. Now it's as simple as subtracting. You start with the actual, subtract the predicted, and that will give you your residual. I like to go back to the visualization to remember that. Sometimes we get confused. Is it predicted minus actual or the other way around? But if you draw it on your little sketch of a graph, if your observation, your actual value is lower than the line, doesn't it make sense that you would have a negative residual? It does. And so you're going to take your actual minus your predicted, and that's going to give you a negative value. You can double check that with the visualization to make sure you're heading in the right direction. Okay, so that is how I approach residual questions. Next, talking about adding variables to multiple regression. This can get really tricky, and so take your time understanding this concept. It's super important, not just now, but for building on concepts later as well. And so one thing we can do is look at quiz 6 and talk about what we would look at when we're holding a variable constant or controlling for a variable. So here you see the same data, but we've now added another predictor, the 5-kilometer time. And so in my mind, I'm taking that same equation, the same idea that we had up here of y hat, the predicted equals intercept plus slope times x, and you can just apply that here. Now here's your intercept. I would just write out plus 849, that's my slope 1, times whatever my x value is for 5-kilometer time. I don't even need to look at the question yet. I'm just setting up my regression equation. And then you would add on top of that humidity slope, 0.26, and then I would just write my x for humidity. I would write out that equation without even knowing what those x values will be yet, because it's helpful to orient yourself to the whole regression before you even look too deeply at that question. Okay, so now we're going to look at this question here. Given that a runner took 20 minutes to complete the 5 km run, I would just stop right there. Now I know one of my x values. 5 km time was something that I was looking for, and I now see that it is 20 minutes. I would put that into the equation that I had just prepared for myself. And the humidity is 50%. And so I would put that into the equation I just wrote for myself. It's asking what the predicted marathon time will be according to the model. And all you have to do now is plug that equation right into your calculator to get that predicted time. A few people, including myself, were tripped up on this specific question because we're used to seeing humidity in terms of percent, and we're used to thinking of percentages in terms of decimals when we use them in equations. In this specific case, we're just entering the number 50. You don't have to convert it to 0.5. You're not going to encounter that kind of confusion on the exam. I just wanted to point it out here in case any other students like me were confused why they had the right regression equation but the wrong answer. So that is one possibility. At this time, I also want to bring up R squared. Now, with R squared, there's really only one phrase that you need to memorize and learn to apply, and that is that R squared is the variability explained by our model. That is the most general way of stating it, and if you can learn to apply that, it will never lead you astray. The important thing is that the word explained means that we have done these calculations in the past. We're not predicting. We're not telling you what it actually is. We're just explaining some of this variance. And I like to go back again to my picture of residuals when I think about this, because it is these residuals that are the variance. We're trying to explain as much of that as we can with our model. And so when we do a regression equation and get an R squared, we're getting this piece of information about how well our model is explaining that variance. In research, especially around the grad students, we kind of use this as a metric for how good the model is. If I create this really complicated model and it only explains 10% of the variance in my data, that isn't going to be super useful if I'm trying to use that to predict anything about this data. I'm only explaining 10% of the variance. Those residuals are going to be huge. But in this case, we're explaining 81% of the variance in the data. That's pretty good in terms of model. And so it's kind of this way to know how our model is telling us about this data, how much weight we should give these predictions that we're coming up with. If you have any other questions about interpreting R-squared, I know it can be a really squishy concept. All of the TAs have different ways of approaching the explanation, so feel free to reach out. We're always happy to go over it again. So that is R-squared. Let's see what else. Okay, the final thing that we want to talk about is seeing whether a variable could be a confounder within data and how to apply all these concepts to a control and treatment situation. So I'm going to start with this image, and then I'm going to get to confounders again in a second. So for me, this is where I missed a lot of questions, or where I had the most trouble on the exam, because I'm used to thinking of regression in terms of this long line that goes on forever in both directions. And when you have only two groups, the control and treatment, it can be confusing to apply those same concepts with this slight alteration. So that's why I'm going to go through this very specifically. And I hope that once I explain it in this way, you won't have to memorize anything, because it will make a little more sense why we look at it this way. So when you have a treatment and a control condition, you may remember when we talked about dummy coding variables that one is going to be represented by 0 in the treatment condition variable, and 1 will be represented by 1. It's going to be this binary variable. And so the information that you are using to answer your test questions will tell you which one is 0 and which one is 1. And it doesn't have to be control and treatment groups. This could be any two groups, but we use control and treatment often because it can help us make some conclusions about how that treatment is having an effect on this measure. And so in this case, control, I will just tell you, was coded as 0. Now, if I asked you to tell me what the intercept is, you should be thinking, what's the definition of intercept? It's the value of y when x equals 0. Aha! She just said that control is 0. And so just because there's only two things on your x-axis doesn't change anything else about the way that you're going to look at and interpret that. If 0 is control on the x is 0, then your y value for control is your intercept. And so in this case, it's going to be about 3.5. Now, what is the slope? And you might think, oh, I don't know if I have enough information to figure that out. Well, actually, if you think about the definition of slope, the increase in y for every 1 unit increase in x, you can see a 1 unit increase in x right in front of you. The control is 0, the treatment is 1. And so the slope is just going to be that change in y value between those 2 points. And so in this case, oh, it's like 0.3 or something like that. So I hope that makes sense. When you're applying these concepts to a control and treatment condition, it's important to remember that your interpretations, your definitions are all the same. The only thing you're changing is that you now have the two groups on the x-axis. And one last point I want to make about investigating confounding variables with data. I think this is a really well represented concept in the handout. So if you don't immediately have some ideas about what a confounding variable might look like in data, I highly recommend you go back to those handouts and reread them. But I just want to specifically remind you, when we add a variable to a regression equation, we are going to be adding information to improve these predictions about the outcome. Now, if we add a confounding variable, think about how that is going to change or keep the same some of these elements that we've been talking about, like the intercept and the slope. How might you expect a confounding variable being added to a regression equation to change that output? And if you have any questions, if you're like, I understand what you're asking, I've reread the handout, but I just don't understand the answer, I don't know how the slope would change, please reach out to the TAs. We would love to go over this with you individually. But I think that if you do go back to that handout, you'll be able to see how Dr. Henry has already built this up in the information you've been given. And I think, too, going back to that will help you to hear it in her words, because that is the person who wrote the test. And so it's going to be phrased and kind of approached in a really similar way, whereas some of the grad students, we may have different perspectives that are useful, but I still think there's a lot of value in going back to those handouts. So that concludes the review. Please, again, don't be afraid to reach out. I will personally be at my computer all weekend, so I'm happy to answer questions, but if you ask me on Monday, just no promises are being made. Please try to reach out before Monday if you have more questions. I'm happy to hear any feedback you have on this review or the past review so that I can make the next review better. You can always reach out to me at emily.sturm@colostate.edu. Good luck with your studies and have a great day.